This is a revision video for P6c Transistors and Logic Gates. Transistors are the main building block of electronic components. There are probably billions of them in your school or house. A computer will have millions of transistors in it. This is the circuit symbol for an NPN transistor. There are three terminals: the base, the collector, and the emitter. A transistor is a type of electronic switch. It's either on or off. When the voltage between the base and the emitter is low or zero, no current will flow in that part of the circuit. But it also means that no current can flow through the collector and the emitter either. So the switch is off. That means that the bulb will not light up. When the voltage between the base and the emitter is high, it allows a small current to flow through the base. This then allows a much larger current to flow through the collector and the emitter, which means that the switch is turned on and the lamp will light up. You can calculate the current through a transistor using this equation. Current through the emitter equals the current through the base plus the current through the collector. Because the current through the base of the transistor is normally very small, it's usually given in milliamps. So you need to be able to convert your amps into milliamps before you answer the question. In this example, we've got the current through the base of the transistor is 0.5 milliamps and the current through the emitter is 0.2 milliamps. What is the current through the collector in milliamps? To answer this question, we need to start by writing down what we know. We know that we are using this equation. We know that the current through the emitter is 0.2 amps, and that is equal to current through the base, which is 0.5 milliamps, plus current through the collector. So the answer is required in milliamps. So you need to start by converting all your quantities into milliamps. 0.2 amps is 200 milliamps. That equals 0.5 milliamps plus the current in the collector in milliamps. Then we do our simple subtraction. 200 minus 0.5 equals the current in the collector, which is equal to 199.5 milliamps. This component is called an LED, or a light emitting diode. It uses special substances called semiconductors. They allow a current to pass through them in one direction but not in the other. When the current flows, light energy is emitted from the semiconductor. Very little heat is produced, so unlike a bulb, it's much more efficient. The efficiency of the LED is about 75%, which is really quite high. Transistors can be used as a switch for an LED. When there's a current in the base, the transistor is turned on. This allows current to pass through resistor 1 and the LED, turning it on. If there's no current in the base, the LED remains off. The base of the transistor would be damaged if a large current flowed through it. So a resistor, R2, is connected in series with it to limit the size of any current in the base emitter circuit. Remember, when there's no current in the base, the transistor's off and the LED's off. When there's a small current flowing through here, it allows a much larger current to flow through this part of the circuit, the collector and the emitter, and that's what causes the LED to light up. Transistors can be miniaturized, or they can be made very, very tiny. There are some certain advantages and disadvantages of miniaturization. The advantages are that computer chips can contain more transistors, making them much more powerful. Smaller components are more energy efficient. Smaller components have a wide range of applications. And smaller components mean that the products contained in them can be made smaller. However, the disadvantages of miniaturization are that the smaller components are more complicated to manufacture, which also means it makes them more initially expensive. Okay, so here are some questions about transistors and LEDs for you to answer. Stop the video and see if you can work out what the answers are. Transistors have got a number of applications. They can be connected together to make logic gates. Logic gates are switches that turn on and off if certain conditions are met. For example, in the central heating system, the boiler turns on if the timer clicks on, or the override button is pressed, or the temperature falls below the thermostat value. The output, which turns the boiler on, depends on the input. Any one of the inputs will make the output turn on. Logic gates are the basis of electronic circuits. The input signal for a logic gate is either high, which is about 5 volts, or low, which is about 0 volts. For a low input, the base current does not flow and the transistor is off. For a high input, the base current flows and the transistor is on. The most common logic gates are the AND gate, the OR gate, and the NOT gate. The AND gate is made from 2 transistors connected like this. Each input is connected to the base of one transistor, here and here. Both of the inputs have to be high for the output to be high. If either one of them is low, then the output will be low. This is the symbol we use for the AND gate, because drawing 2 transistors out in that circuit can look quite complicated. But if we use this, we can do much more complicated circuits with simpler symbols. This is called a truth table for the logic gate. It shows the inputs A and B, corresponding to these ones here, and then the output. Now we saw before that both of the inputs have got to be high for the output to be high. So if one of them is high, then the output will be low. You need both of the inputs to be high for a high output. This is the OR gate. It's formed again from 2 transistors, but they are connected in a different way. They are connected so that if the output is high, when either or both of the inputs are high. This is the symbol we use for the OR gate, and this is its truth table. Again, the columns A and B represents the inputs A and B, and this column represents the output. And now if both of the inputs are low, the output will be low. However, if you have one of the inputs that's high and one is low, the output will be high. And then again, if you have both inputs high, the output will be high. This is the NOT gate. In the NOT gate, the output is the opposite of the input. So truth table is quite simple. It only has one input and one output, so we've got 2 columns. If the input is low, then the output is high. If the input is high, then the output is low. This is the NAND gate. It's formed from 2 logic gates, the AND and the NOT gate. The output of the AND is connected to the input of the NOT. Its outputs are opposite to the AND gate, so both inputs have to be high for the output to be low. So if you think about what the AND gate does, this one does the opposite of that. So in a normal AND gate, both of these would have to be high for a high output. But because this one does the opposite, when both of them are low, this gives us a high output. In a normal AND gate, a low and a high input would give us a low input, but as this does the opposite, it is high. And then again, in our normal AND gate, 2 high inputs would give us a high output, but this one does the opposite, so it's low. This is the NOR gate. It's formed from, again, 2 logic gates, the OR gate and the NOT gate. And it works in quite a similar way to the NAND gate. So you think about your normal OR gate and what it does, and this one does the opposite of that. So in an OR gate, a normal OR gate, you would need at least one of the inputs to be high to give you a high output. Normally, if they were both low, you will get a low output, but in the NOR gate, it's high. Normally, if you have one low and one high input, you would get a high output. But as this does the opposite, it gives us a low output. And then in the OR gate you would expect two high inputs to give a high output, but this time it is low because it does the opposite. Okay, stop the video and have a go at these questions about the logic gates. And that brings an end to this revision section on transistors and logic gates.